National 5 Physics, welcome back to another episode from Mr. Bill's Physics. I've just put on the kettle for another cup of tea for another day in lockdown. But today I'm going to be talking to you about another installment in the Properties of Matter course, and that is temperature, and specifically the Kelvin scale. Now I'm going to go through the PowerPoint in a second, but as this begins to boil, I'm going to have to speak a little bit louder. But why am I boiling a kettle and talking about Kelvin? Well, when I put that water in there, it was probably about 293 Kelvin. Alright? At a kind of freezing point of water, it's 273 Kelvin. Now, we only use degrees Celsius because we have those 2 points, melting point or freezing point, and boiling point, 0 degrees and 100 degrees. So I'm boiling this water at about 293 Kelvin. Alright, because the water is probably about 20 degrees Celsius, probably even lower than that, probably 283 Kelvin. Now, when this boils, it's going to go up to 373 Kelvin. Alright, so when you change the Kelvin scale, you're actually changing in the same units as the degree scale. So 1 Kelvin is 1 degree Celsius. And the only difference is this fancy number, 273, very odd number, but a very unique number. And I'm going to talk a little bit more when we go into the PowerPoint. But I want to tell you a little bit about the things that I drink and the things that I enjoy during lockdown. So one of them is this thing here. Now, if you like tea, I like this one. It's biscuit brew. Biscuit brew. It tastes like a biscuit, but it's a tea. Come on, you gotta love this. So I would go to Morrison, Sainsbury's, you should have it. Biscuit brew. Love that chat. And if I want some juice, one of the juices that I like is pink grapefruit. Some people are like, no, surely not, Mr. Bill. No, I do. I like pink grapefruit with barley. And you can't really beat some coffee. Some Taylor's coffee. Come on. Taylor's ground roast 4 coffee. Brilliant. You can't beat that. Now, kettle's just boiled. I'm going to just pour it into my favourite mug, my Loch Carron mug. Alright, all the way up in the north of Scotland. Wonderful pottery up there, okay? Selfless promotion for all of these products, okay? I'm not getting paid or sponsored by any of them, but if they are listening, which I don't think they are, I would love a whole box or tray of biscuit brew. Now, I'm going to put one of the tea bags in. Alright, I'm going to pour myself a wee hot cup of tea. And I'm ready to dive in to another episode of Mr. Bull's Physics. I'll see you on the PowerPoint in 3, 2, 1, and go. Alright, National 5, welcome back to another episode of Mr. Bill's Physics. I hope you enjoyed my little talk about beverages, but now it's time to move on to properties of matter. Now, you know the drill. Like, share and subscribe. That is just the consistent message in lockdown for you guys in National 5. But to move on, we're going to be talking today about properties of matter, but specifically the Kelvin scale. Okay, so the Kelvin scale. Now, a couple of things we need to talk to before we get there, but this is a really important scale. If you take physics into engineering, or even if you do straight physics, you will use the Kelvin scale more than any other temperature scale. More than degrees Celsius. I mean, we never use Fahrenheit, but we always use the Kelvin scale. It's a really important scale. Now, what's our learning intentions? To introduce the properties of matter, volume, density, pressure, and temperature. We're going to be doing temperature and volume today. We have talked about pressure and density last week. And we're going to be able to understand why an object experiences buoyant. No, we're not really going to be doing that today because we've kind of been looking a little bit beyond that. Now, the first thing we need to look at is volume. So, if I was to ask a question, how many centimetres cubed are there in 1 metre cubed? How would we find that out? Well, if you were to actually have a metre stick and kind of box out a metre by metre by metre, it's actually fairly large. And centimetre cubes, I always remember from primary school, the wee centimetre cubes used to count. We know there's 100 centimetres in 1 metre. So if we were to time 100 times 100 times 100, which is say at the bottom here, you get 1,000,000 centimetres cubed. Alright, which is the same as 1 metre cubed. So 1 metre cubed, with the volume wise, is 1,000,000 centimetres cubed. Alright, so you obviously can imagine trying to put all those centimetre cubes into a metre cubed. It's going to be a lot, alright? But that's just making sure you're aware of making sure that everything you do with volume is in metres. Everything is in metres, alright? And you can't just think that, oh, if something's 1 metre cubed, that means oh, to get into centimetres, it's going to be 100 centimetres cubed. No, it's not. It's much, much bigger. It's 1,000,000 centimetres cubed. Okay, so make sure you remember that. So that's the little summary there. Please make sure that your volumes are always in meters. Okay, some of us, I think last week we're putting in centimetres when we were trying to find out areas for pressure and force and area. Always meters. Okay. Now, let's talk about temperature. The temperature scale we're looking at today is called Kelvin. Now, actually, fun fact, I have a little brother called Kelvin. All right, he's about, what age is he now? He's a good bit younger than me now, but his name is Kelvin, and you might recognise things like Kelvin Grove or Kelvin Grove Art Gallery or the Kelvin Building, and they've got University of Glasgow. There's lots of things in the West End of Glasgow that have the name Kelvin in it, and it's named after a famous physicist who, Lord Kelvin, who kind of discovered this scale. All right, so it's very similar to the degrees Celsius scale. Now, the degrees Celsius scale is only used for two things. One, really, to point out the melting and the freezing point of water, which is 0 degrees Celsius, and then also the kind of boiling point of water, which is 100 degrees Celsius. It's just a nice number, so that's why we have degrees Celsius. But the Kelvin scale is actually more widely used in the physicist world. So the Kelvin scale starts at 0 Kelvin. All right, we can't get anything below 0 Kelvin. So 0 Kelvin is the lowest temperature you can possibly achieve on Earth, or in the universe for that matter. So 0 Kelvin is known as absolute zero. And absolute zero is basically where, and we're going to come on to this in future weeks, where particles stop moving. Because theoretically, if particles don't move, then they're not going to hit anything, which means they're not going to create any energy, any heat energy, and therefore there'll be no heat. So that Kelvin scale at absolute zero is minus 273 degrees Celsius. So minus 273 degrees Celsius is the lowest temperature anything can be in the universe. All right? Now, if you want to get from the Kelvin temperature from the Celsius temperature, what you need to do in the yellow box here is saying Kelvin temperature equals the Celsius temperature plus 273. And to get from Celsius from the Kelvin, it's Celsius temperature equals Kelvin temperature minus 273. And a little hint is that the Kelvin number will always be higher than the degrees Celsius number. All right, so that's a wee hint. Kelvin number should always be bigger than the degrees Celsius number. Now, remember the cosmic microwave background radiation, which some of you keen physicists might know of, is 3 Kelvin, all right, or minus 270 degrees Celsius. And the reason why the universe is slightly heated, but by 3 Kelvin, is because it's still a remnant from the Big Bang. Kind of when I was talking about the kettle there. If I was to leave that kettle for another 10 minutes, it would probably still be a little bit warm. And that's the same idea as the Big Bang. So it's quite a cool thing to think about. Now, just a wee note that the temperature difference of 1 degree Celsius is the same temperature difference as 1 Kelvin. Okay? So if we were to take EH equals CM delta T, we could still use Kelvin because it's the same change. 1 degree Celsius is equal to 1 Kelvin. All right. Now, what I want you to do is take a wee look at this. I would like you to pause the video and I'd like you to calculate out this table. Okay, so you know that the temperature Kelvin scale must always be bigger than the degrees Celsius. But using the yellow box just back up above, I would like you to complete this table. Okay, do you add 273 or do you minus 273? Pause the video and I'm going to continue in 5 seconds. Go. Okay, well done. Okay, I'm going to move on to the answers. So this is what it should be. And as you can see, the degrees Celsius is always lower than the Kelvin scale. And if you want to find temperature, you're going to have, and you've got the Kelvin scale, you're going to have to minus 273. And if you've got temperature and you're trying to find Kelvin, you're going to add 273. Okay, so they should all be corresponding to one another. And make sure you remember you cannot get anything less than minus 273 degrees Celsius. So as we said, we're going to talk about absolute zero a little bit later. But absolute zero is when there's 0 Kelvin and minus 273 degrees Celsius. And it's a very odd state to be. And we can try and get close, but we'll never get to 0 Kelvin on Earth. It's too theoretical for us at this stage. But more of that chat later. And National 5, that is it. That's all we have time for today. So hopefully that's nice and easy. The questions are going to be on pressure and also
on Kelvin Scale, okay? So a little bit of revision from last time as well. Okay, National 5, well done. And I'll pass over back to myself.
Well, that's us for today, Mr. Bill's Physics channel. And wherever you are, if you're drinking a cup of tea or if you've got a flask of water or juice, I want you to raise that. All right, let's raise a glass to 2021. All right, we're going to get through this together. Cheers. Cheers. Have a good one, National 5.